How the OSI Model Works.com. The OSI Model, part of LearnTCPIP.com. The OSI Model. In this section we'll talk about what the OSI model is, why it is used for analysis and comparison of different protocol families. We'll talk about the importance of its modular design, and then we'll look at each one of the 7 layers individually. The Open Systems Interconnect, or OSI model. Now, the OSI model was created by an organization called the International Standards Organizations, so the ISO created the OSI model. And it is a model, and as a model, it is used to help us understand how network protocols and network components can be made and can be made to work together. The thing about the OSI model is that, in a sense, you can't buy the OSI model. You can't go to the store and buy an OSI model for networking. It's a model that allows us to analyze network protocols, compare how they work, and also, when we get into trouble, troubleshoot networking problems. Protocols. In networking, we talk a lot about protocols. We say lots of things are protocols. So let's get a definition. A protocol is a set of rules or guidelines that control or govern the communication between different networking devices. And the truth is when you're setting up networking and using networking, you're never using a single protocol. You're probably using multiple protocols, sometimes many protocols at once. And when you do set up networking, you are probably using, again, not a single protocol, but you're probably using a suite or family of protocols. For instance, if you're using TCP/IP, you're really using what's called technically the Internet suite of protocols. And one protocol in the family is TCP, another protocol in the family is IP. You'll probably be using both of those. But in addition to TCP and IP, you're probably going to be using UDP. You might be using ARP. You're probably going to be using ICPM. You might be using HTTP. You'll be using numerous protocols within this protocol family. Now, this is not the only protocol family. There are a lot of other protocol families. For instance, in the old days, the NetWare suite of protocols, because NetWare is now using TCP a lot more, but they had a set of protocols that was generally referred to as IPX. But it wasn't just IPX, because IPX is a single protocol. In addition to IPX, there was SPX, there is NCP, again, numerous protocols part of that protocol family. And when you set up your network using IPX, you're using all those protocols. In addition, another example of a protocol family is the IBM SNA protocol family that's used on the mainframe computers. Again, multiple protocols within that family. And why the OSI model is so important is that when you are setting up networks with multiple protocol families, and it's quite common, you need a common way to analyze different protocol families, to compare protocol families, and then to troubleshoot them. The 7 layers of the OSI model. Now, whenever you see a picture of the OSI model, you always see a block diagram with 7 different blocks. These are called our 7 different layers of the OSI model. And to understand what these blocks do, you have to understand what the whole diagram is. This is what we call the stack. Now, the stack, the OSI model incomplete, represents, now remember, it is a model, and that model represents all the specifications, the functions and activities that need to occur in networking. So if the stack represents all the functions that need to occur, each layer represents a group of related specifications, functions, or activities, again, to have successful networking. Now we'll see that we have the famous 7 layers: the physical layer, the data link layer, the network layer, the transport layer, session, presentation, application. Think of each one of these, for instance, like the physical layer, a set of specifications, related specifications that are part of networking. Now, the physical layer itself, the specifications that are part of that, will not provide successful networking. It needs the specifications and the functions and activities of all the other layers of the OSI model. Now, in this presentation, we'll go through the different layers one by one and talk about the specifications, functions, and activities specified at each layer. As I mentioned before, one of the important things we want to do with the OSI model is to use it to analyze and compare existing protocol suites. Now, in the diagram here, we have the TCP/IP suite of protocols compared against the OSI model. Now, we will see that by looking at the model and the OSI model and the TCP/IP suite, that the network layer and the IP protocol matches up. Because of that, we would expect the IP protocol to do the same sort of activities, functions, have the same specifications as the network layer would. So the question is, well, is each layer in the OSI model a protocol? And do they always match up exactly? Well, sort of. The OSI model, analysis and comparison. This is one of the primary uses of the OSI model. Now, in this slide, we can see in the middle that we have the OSI model with its 7 different layers, and then surrounding it we have different protocol suites. On the far left we have the NetWare family of protocols. We have next to that the TCP/IP suite of protocols. Going to the right we have the IBM SNA family of protocols, and way on the far right we have the AppleTalk family of protocols. Remembering that each layer of the OSI model specifies a set of related specifications, activities, and functions. Let's first take a look at the IP protocol in TCP. Now you'll notice that the IP protocol in the TCP/IP suite of protocols matches up to the network layer in the OSI model, but also notice that in the NetWare family of protocols they use a different protocol called IPX. But because both these protocols are considered network protocols, we'd expect them to have similar or provide similar specifications, functions, activities. Doesn't mean they'll do it exactly the same, it just means that they will have similar purposes. Now, take a look at in the TCP stack the presentation and session layer. Now notice in this situation protocols like FTP, SMTP, NFS, and HTTP actually perform the functions of not a single layer of the OSI, but also of 2 layers, of both the presentation and session layer. Also, take a look at the IBM SNA stack. Now, if you focus in on the transmission control protocol on the IBM SNA stack, you'll see that it's kind of in between the network layer and the transport layer on the OSI model. What this means is that when the IBM SNA protocol, the transmission control protocol, was created, that it had or provided some of the activities or functions that were considered part of the OSI model network layer, and it provided some of the functions that are considered part of the OSI model transport layer. The truth is that the SNA set of protocols was created before there was an OSI model, and that's why that's different. Now, there is no requirement that any protocol matches up exactly to the OSI model, because the OSI model is essentially our guide when we want to analyze and compare and later down the road troubleshoot connectivity problems between different protocol families. The OSI model, modular design. Now remember, the OSI model in total, the complete stack, represents all the activities, functions, and specifications that need to be in place to have networking. Also remember that each layer of the OSI model has a group or a subset of the specifications, activities, and functions that need to occur for successful networking. And in our previous diagram we saw that in many cases each layer has a corresponding protocol. Now, in broad definition, we can call just about anything a protocol, and in this presentation we're going to call everything a protocol, because we have in this case the TCP/IP stack listed out here. HTTP is a protocol, TCP is a protocol, IP is a protocol, and we're going to call Ethernet is a protocol. Now remember that each layer may correspond exactly to a single protocol. Sometimes a protocol, in the case of HTTP here in this presentation, will actually provide the functions of 2 different layers of the OSI model. Also remember that in the case of SNA, that an SNA protocol doesn't match up exactly to a single layer and may actually provide functions or specifications that are part of 2 different layers. The next thing we're going to talk about is the idea that each layer really only interacts with the layer immediately above it and the layer immediately below it. Now, in our example with TCP/IP, let's take the example of Ethernet. Now, Ethernet corresponds to the physical and data link layer of the OSI model, and it will only correspond with IP, which means that when Ethernet has information it wants to pass up the stack to another protocol, it has to pass it to IP. It cannot pass it right to the application. It cannot pass it to HTTP. Likewise, in the case of TCP, what does it do? When it is sending information, it passes it down the stack to IP, never right to Ethernet. Likewise, when TCP receives information, it passes it to, in this case, HTTP, never really the application. In this case, the application would be, for instance, a web browser. The layers of the OSI model. Now remember, the complete stack of the OSI model, all 7 layers, represents all the specifications, functions, and activities that need to occur to have successful network communication. In this next section, we're going to look at each layer individually and look at the specific set of specifications, functions, and activities that that layer is representative of. The physical layer. Now, what is the definition of the physical layer of the OSI model? Well, it's a set of specifications for all the physical components used in networking. And what is an example of these physical layer components? Well, for instance, it's the cabling, the type of cabling, the interconnection methods, the connectors, if you will, how you bring the cabling together, the data encoding method. Now, when we talk about data encoding, this is the method that the zeros and ones, the bits of the data, are transformed into electrical waveforms. Also, it is electrical properties, the voltages used, those sorts of things. Now, what's an example of some physical layer specifications? Well, for instance, Ethernet's a physical layer specification. Also token ring, also FDDI, and there's numerous other ones. Now, it's important to keep in mind that from an OSI perspective, does the OSI model really say, oh, you have to use Ethernet, you have to use token ring, you have to use FDDI? No, it doesn't. It just says that if you want to be a physical layer specification, you have to specify a type of cabling. You have to specify interconnection methods. You have to specify data encoding electrical properties. And since all these different protocols or specifications specify these same things, they are considered physical layer specifications or physical layer protocols. Physical layer comparisons. Now let's take a look at the details of 2 different physical layer specifications. One of them is for Ethernet using thin coax cabling. The other one is for token ring running at 16 megabits per second. Now you will see that the type of cabling is specified by Ethernet to use an RG58 coax. Not a lot of people are using that right now, but it is a specification, one that has perhaps more historical importance than any other. And then when you take a look at token ring at 16 megabits, you see that it specifies the use of category 5 twisted pair. Connectors, they use different types of connectors, BNC for Ethernet, RJ45 for token ring. They have different encoding techniques, they use different interconnection methods, and they run at different speeds as far as their electrical properties. But the important thing is they are both physical layer specifications. They both specify the same sorts of stuff. They both specify cabling, connectors, interconnection methods, data encoding methods. Now they have different requirements for each, but because they have the same type of specifications as the OSI model physical layer, they are considered physical layer specifications. The physical layer. Well, what do physical layer components do? Well, they are generally the specifications for the physical components of the network, the cabling, the interconnection methods, things like that. We talked about some examples, Ethernet, token ring, FDDI, and if the question is, where are they on my computer? Where are your physical layer components? Well, really, that's your network interface card, that's your cabling, those would be your hubs, those sorts of devices. The data link layer. Well, what does the data link layer do, or what do components that are considered data link layer do? Well, they place data on and retrieve data from the physical layer, as in the network cabling. In addition, they do provide error detection capabilities, and we'll see that coming up. Now, I've got some examples of some data link layer specifications or protocols. It's Ethernet, token ring, FDDI. You'll remember that they were also physical layer specifications. In the case of data link physical specifications, generally a single protocol or a single specification will provide services that are associated with both the physical and data link layers. The data link layer. Well, what do data link layer components do? Well, sometimes you will see that the data link layer is subdivided into two sublayers, one called the Media Access Controller MAC layer, and the other one is called the LLC or Logical Link Control layer. We're going to, in this presentation, just talk about all the functions of the data link layer in one. One of the functions it does is it provides addresses to network devices. These are sometimes called our MAC addresses or hardware addresses, and we'll talk about those coming up. Also, a data link protocol will create the data frame. This is really what we could consider a packet. This would be our Ethernet packet or our token ring packet. Also, one of the key functions is that the data link layer protocol will give the data bits to the network interface card, because the computer, remember, stores all data as a string of zeros and ones. But what the data link layer component needs to do is to take these zeros and ones and turn them into an electrical waveform that can be transmitted over the wire. Now, another thing the data link layer components will do will control the network interface card or NIC card's access to the media, because we have a situation where potentially all the NIC cards could want to transfer information at the same time, but on a single wire we can only have one NIC card transferring information at a time. So there has to be a way to control access to the wire, and that's the job of the data link layer or the data link layer components. Also, one thing the data link layer has to do that's very important is to detect errors in transmission, so that if the data is corrupt when it gets to the receiver can tell this. The data link layer and addressing. Now, one important function of data link layer components is to have or set up network addresses, because we're going to have a situation where we have many network devices on the same networking system, and there has to be a way to identify the proper machine you're sending data to. Kind of like telephones. Each telephone has to have a unique phone number. Each networking component has to have a unique address. Now, in most cases, this unique address is burned into the network interface cards by the manufacturer. In many cases, in the case of Ethernet and token ring, for instance, it's a 6-byte address. Now, this address is sometimes called the MAC address, the hardware address, or the NIC address. The link layer framing. Now, one thing that a data link layer component needs to do is to frame the data. Now, the data link layer component will receive information from an upper layer protocol. For instance, in our example, we'll say that the data link layer component is Ethernet, and the upper level protocol is IP. IP will hand Ethernet some information that needs sent on the network. Then Ethernet will then encapsulate that IP information in a data frame, and it will add information in that data frame that will allow it to properly deliver the packet. Now, that packet is called a data frame. Now, sometimes the terminology is thrown back and forth. It's a packet or it's a frame. We can just think of those as the same thing. But the Ethernet header information has specific fields and specific functions. Now, we're looking at Ethernet in this example, but keep in mind that token ring has a very similar format, because token ring does the same sort of things. It's slightly different, but again, because they're both data link layer components, they do and provide similar capabilities. Now, in an Ethernet frame, the format is where there's the first set of bits are a header. The header information has no real data. It just allows the sender and receiver to sync up. And then after the header information is the destination MAC address. This would be the address of the network card that this packet is destined for. Then after that is the source MAC address. This is the MAC address or NIC card address that is sending this frame. So there's the to address and the from address. Inside there's a frame type. This just identifies the contents of the packet, and then finally at the end of the packet we have some error check information. The data link layer, media access control. Now, one of the key responsibilities of data link layer components is to take the data frame, which is the data we want to transmit. It, of course, because it's data, is a bunch of zeros and ones, and then transfer that to the NIC card, where the NIC card will then turn that into an electrical waveform to be sent out on the network cabling. Now, there is one important issue in that there could be a situation, or I guess in most situations, there'll be more than one network interface card or more than one network device that wants to get access to the media to send data. Because we're on a shared media, all the network components are in the same cabling system. Only one computer or one device can send a packet at a time. So there has to be a way to control access so only one device can be transmitting data at one time. Now, a data link layer component has to have, or a data link layer specification has to have, a way to control access. Now, there are a couple very popular ones, or very commonly used ones. The one that Ethernet used to control access is called Carrier Sense Multiple Access Collision Detection, or CSMACD. Now, token ring networks use a token passing methodology. Also, FDDI uses token passing. Now again, the OSI model doesn't mandate a specific method for controlling access to the media. It just says that if you're going to be a data link layer specification, you have to have a way of controlling access to the network. The data link layer, error detection. Now, one method of error detection that data link layer components uses is cyclic redundancy check, or a CRC. Now, this is done in the following manner. Before a packet or a frame is sent out, there's a mathematical formula that is used to calculate a unique value that represents the data in the frame. Then that unique value is added to the data frame and then sent out with the packet. When the packet arrives at the destination computer uses the same formula on the data to determine the CRC number. It takes a look at the CRC number that it is calculated and matches it to the CRC number that was included on the frame. If they match, that means the data has not changed. If they don't match, and it doesn't matter if it's a little bit off or if it's a lot of bit off, that means the data has been changed. And because it's been changed, then the frame is considered bad and it will be discarded. Now you will notice that this is an error detection method. This is not an error correction method. At this layer, all we're going to do is detect errors. If the packet's bad, we'll throw it out. Data link layer, review. What do data link layer components do? Well, remember we have the data link layers components responsible for network addresses. These are our MAC or hardware addresses burned into our NIC cards. Remember, they're responsible for creating a thing called a data frame. They take the information that's going to be transferred on the network, put it in a data frame. Remember, that data frame has things like the source and destination MAC addresses, which will be needed to properly deliver that packet. Also, remember, this responsibility of data link components is to deliver the frame to the network interface card, the physical layer components. Then the physical layer components will take that string of zeros and ones, which is really the frame or packet, and then turn it into an electrical waveform and send it out onto the network. Also remember, part of the data link layer is there has to be a method to control access to the physical cabling, so we don't have multiple devices trying to communicate at the same time. And also remember, data link layer components are responsible for detecting errors in transmission. Now again, the OSI models doesn't mandate a specific method to do these things. It just says that if you want to be considered a data link layer specification or protocol, you need to have a method to handle these things. So in the case of Ethernet, well, Ethernet does all these things. In the case of token ring does all these things. They do a little bit different, but they do provide all these functions and activities. Now, where are data link layer components on your machine? Well, they're your network interface card, and also they're the driver that's associated, the software driver that's associated with your network interface card. The network layer. What does the network layer do? Well, it provides a network-wide method of addressing and a mechanism to move packets between different and multiple networks. And really this process of moving packets between different networks is called routing. Now, example of network layer protocols, in the case of the Internet suite of protocols, the TCP/IP suite of protocols, the IP or Internet protocol would be considered a network layer protocol. In the case of network, it would be IPX. Network layer, network-wide addressing. Now, when we talked about the data link layer, we talked about MAC addresses and how these MAC addresses, sometimes called hardware addresses or NIC card addresses, are unique addresses that are burned into the network interface cards. Now, these addresses are used to communicate and send data frames between devices that are in the same physical segments or the same subnets. Now at the network layer we have another address, and we call this the network address. Now this is a network wide address, and it is used to transfer data across multiple subnets or multiple physical segments. These are used by routers to forward packets to different networks. Now, an example of this is the IP addresses we use in the TCP/IP protocol, and of course we use them on the internet. Network layer routing. Now, one of the key tasks of a network layer protocol, according to the OSI model, is to route packets. Now, routing packets is the process of intelligently moving packets from one network to another. Now, in this example, we have the red computer on the left, and we have the blue computer on the right. When the red computer wants to send a packet to the blue computer, it will forward it to the router. And then the router, based upon information it has about the network, will then have to decide where to forward that packet in order to get it to the blue computer. And that's the process of routing. Network layer review. Now, any protocol that provides network-wide addressing and has mechanisms to move packets between different networks that provides routing would be considered a network layer protocol. Now again, the OSI model doesn't specify that you have to do it this way or that way. It just says that if you do these things, you are considered a network layer protocol. Now, where would network layer protocol software be? For instance, if you were running TCP/IP, it would be the TCP/IP software on your computer. The transport layer. Well, what does the transport layer do? It provides end-to-end communication and reliable data delivery. Now, you will notice I did say reliable data delivery. It can't really guarantee data delivery, because if the cable gets broken or cut or something, then the data is not going to get there. But it'll try to provide reliable data delivery. Now, examples of transport layer protocols would be, for instance, in the TCP/IP suite of protocols, it would be TCP, or the Transport Control Protocol. Another protocol that's considered transport layer, that's part of the TCP family of protocols, would be UDP, or User Datagram Protocol. Now, what do? Well, transport layer protocols will receive data from upper layers from the application and then segment it in smaller pieces. They will also provide transmission, error detection, and possibly correction. The transport layer and reliable data delivery. Now, an important point has to be made about the relationship between the transport layer and the upper layer protocols. The transport layer provides reliable data delivery to the session, presentation, and application layers. Now, when I say reliable data delivery, that is not guaranteed delivery, because, of course, if the cable is broken or something, there's nothing that can be done to transfer the data. But what the transport layer does is it isolates the upper layer protocols from the details of the data transfer. In most cases, the activities of the session layer, the presentation layer, and the application layers are done by a single application. And what that application does when it wants to transfer data is it hands that data off to the transport layer. And then the transport layer is responsible for delivering the data. And from the application's perspective, it really doesn't know anything about the layers below the transport layer. It just knows that it's given the data to the transport layer, whatever the transport layer is, and then the transport layer takes it from there. It isolates the application that makes the data from the way the data is transferred. Because when an application, say like a web browser, TCP data to be transferred, it doesn't really know if Etherlink is down at the data link layer, or if Token Ring or FDDI, nor does it care. It just knows that it's given data to the transport layer, and the transport layer is responsible to deliver that data because the transport layer provides reliable data delivery. Transport layer segmentation. Now, one thing a transport layer protocol will do will receive data from the upper layer protocol or application and then segment it. Now, one thing about packet size is that the packet size is generally dictated or controlled by the data link layer. It's part of the specification of the data link layer. Now, in the case of Ethernet, the maximum packet size is 1518 bytes, including the CRC. Now, there could be a situation where, for instance, a web server needs to send a big graphics file to a user. Now, that graphics file will be given to TCP. TCP will see that the maximum packet size is 1500 bytes, much less than the size of the file. It will take the file and segment it or divide it into pieces and then send a piece out in each packet. Now, the receiving station, the TCP software on the receiving station, will then take those individual pieces of the file it receives in multiple packets and then recombine them, and then in this case give it to the web browser for display. Transport layer. Error detection and correction. Transport layer protocols can, and I stress can, provide error detection and may provide error correction. Now, when we talk about protocols, we mostly have this discussion about protocols at the transport layer, but really it is valid at any layer. Protocols can be classified in one of two groups. Protocols could be considered connection-oriented protocols or connection-less protocols. Connection-oriented protocols send data back and forth in a tracked and sequenced manner. Now, before the devices send data, they create a connection. They exchange configuration information. Then each time a packet is sent, it is acknowledged by the receiving station. Now, if a packet is lost somewhere along the lines, then the sending station resends it. And this is most often used during data transfer. Now, examples of connection-oriented transport layer protocols would be TCP in the Internet Suite of Protocols and SPX in the IPX Network Suite of Protocols. Now, also at the transport layer, we could have a connectionless protocol. In this case, no connection is set up, and packets are sent out, and if they're lost, they are not resent. Now, examples of when we would use a connectionless protocol would be something when we're doing a broadcast or an announcement packet. Now, examples of this, again, in the Internet Suite of Protocols would be the UDP protocol. In the case of the Network Suite of Protocols, it would be IPX. Transport layer review. Now remember, transport layer protocols will receive data from upper level protocols or applications and then segment that data based upon the maximum packet size. Now remember, the maximum packet size is part of the data link layer specification. Also, transport layer protocols will provide transmission error detection and perhaps correction. Now, if you wanted to find out where your transport layer software was on your computer, well, in the case of a computer configured with TCP/IP software, remember transport layer is the TCP protocol, so that would be part of your TCP/IP software. The session layer. What does the session layer do? Well, it allows for applications to maintain an ongoing communication session. Now, examples of this are the net bias protocol or the network core protocol. And really, what do session layers components do? Well, they manage user sessions and track user sessions. Session layer and user sessions. In this section, let's talk about a session layer protocol, the net bias protocol. If you are familiar with Microsoft networking and Windows networking, you have probably been using the net bias protocol. Now, the net bias protocol manages user connections. This is a software that in a sense allows us to share resources. This would be a shared folder or directory or a shared printer, and then manages the connections and let us connect to those shared resources. Now, where is this software on your Windows computer? Well, if you're using Windows, some version of Windows, this would be your workstation or your server service software. Now, if you're in a network environment, this was a software that was traditionally called the redirector or the requester. I guess these days this would be your Windows client for network. The presentation layer. Well, what does the presentation layer do? Well, it provides common data formatting between the communicating devices. Now, an example of this would be the multi-purpose internet mail extensions or the MIME protocol. And this makes sure that the receiving station can read the data that is sent by the transmitting station. Now, where does the software reside? Well, in the case of the MIME, it resides inside your email client. If you are connecting to shared files and shared printers, this is part of your workstation and your server service software. The application layer. Well, what does the application layer do? It gives end user applications access to network resources. An example of this is the workstation and server service in Windows, or the Windows client in NetWare. Now, this application layer does not include end user applications. So this is not Word or WordPerfect. This is the software that gives you access to the shared resources and shared printers. And again, it's your workstation service or your client, your network client. Now, one thing we should be aware of is that when we talked about the data link layer and the network layer and the transport layer, it seemed there was a single protocol that matched up to the network layer. For instance, the IP protocol performed the functions of the network layer. The TCP protocol performed the functions of the transport layer. In many cases, the networking client performs the top three functions: the session, presentation, and application. So in many cases, you'll see these combined into, in a sense, a single layer. The OSI model review. Now remember, we talked about the stack, and remember the stack, all 7 layers, represent all of the specifications, functions, and activities that need to occur in order to have successful networking. Now remember, each layer represents a group or a subset of related specifications and functions that need to occur. And each layer has a different set of related specifications, functions, and activities. Now remember, the OSI model doesn't specify exactly how a protocol should do things as far as what cable specification it has. It doesn't specify how error correction needs to be done. It doesn't specify how addressing needs to be done. It just specifies that it must be done. And this model, the OSI model, then gives us a great tool that allows us to analyze networking problems by knowing what layer the problems could occur at. It gives us the ability to compare different protocol families. And also, when problems occur, it gives us a great troubleshooting tool to understand how protocols work together. Because if you know the functions of the layers, then you can analyze, compare, and troubleshoot. And one thing to know, as network legend Dan Knowles said, is we spend 90% of our time rolling around the bottom 4 layers. And as a network technician, that's really where we spend our time, because the bottom 4 layers, we have the physical layer, that's the cabling and interconnection devices. The second layer, data link layer, that's where we have our network interface card and our network addressing, or I should say our MAC addressing. The third layer is a network layer, which we have, for instance, our IP addressing, and then the transport layer, the 4th layer, that's where we have reliable delivery. And that's, as technicians, where we spend most of our time.